Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Fuad bin Ibrahim. Matrix number S66275. Today I will present the answer for group assignment question 2.4 flow sensor linearization. For part A, I use the fixed point iteration method to solve the equation. The original equation is the ln of x plus x equal 3. First, I rearrange the equation into x equals 3 minus for the natural ln of x, which is the required form for the fixed point iteration method. I start with the initial guess of 2.000, then I repeatedly substitute the previous value into the equation to calculate the next approximation. After each iteration, I calculate the approximate relative error to determine whether it was less than required stopping criterion of 0.05%. The error gradually decreased with each iteration, showing that the solution was converging. After 9 iterations, the approximate relative error became 0.0226%, which is below the required limit. Therefore, the final root obtained using the fixed point iteration method is 2.2080. Now for part B, I solve the same equation using the Newton-Raphson method. The function is the ln of x plus x minus 3 and its derivative is 1 divided by x plus 1. I used the same initial guess of 2.000 and applied the Newton-Raphson formula to calculate the next approximation. Unlike the fixed point iteration method, Newton-Raphson used both the function and its derivative, which allow it to converge much faster. After the first iteration, the approximation became 2.2046. After the second iteration, it became 2.2078. And after the third iteration, the value converged to 2.2079. The approximate relative error at this stage was 0.0045%, which is lower than the required stopping criterion of 0.05%. Therefore, the final root obtained using the Newton-Raphson method is 2.2079. Now for part C, the most stable method for this type of nonlinear sensor correction is Newton-Raphson method. It is more efficient because it reaches the required accuracy in only 3 iterations, whereas the fixed point iteration method required 9 iterations. This is because the Newton-Raphson method uses both the function and its derivative to estimate the next value, allowing it to converge much faster. On the other hand, the fixed point iteration method is simpler to apply because it does not require the derivative, but it converges more slowly. Therefore, for this nonlinear sensor calibration problem, the Newton-Raphson method is the better choice because it provides faster convergence, require fewer iterations, and achieve the required accuracy more efficiently. Now I will present the result and comparison between the manual calculation and the MATLAB simulation. For the fixed point iteration method, both the manual calculation and MATLAB produce almost the same final value, which is 2.2081 with very small error. For the Newton-Raphson method, both methods also produce the same final value of 2.2079 with MATLAB achieving 0% error. Overall, the manual calculation and MATLAB results are very similar, which shows that the calculations are correct. Comparing the two methods, the Newton-Raphson method is better because it reached the solution in only 3 iterations, while the fixed point iteration method requires 9 iterations. Therefore, Newton-Raphson is faster and more efficient for solving this problem.
Assalamualaikum warahmatullahi wabarakatuh. Nama saya Hazrin Azhar University. Jadi sekarang saya akan membincangkan tentang chapter 3.5. Macam yang kita dapat tengok problem statement dia, kita dapat tengok humidity data dia berada di T sama dengan 7 minit was lost due to firmware update. Kita kena gunakan interpolation to recover the missing value. And the methods that has been used is third order Newton divided difference and third order Lagrange interpolation. And next we are going to move to manual calculation and MATLAB verification. Next, we move to the result. As we can see, kita dah kira menggunakan Newton method and Lagrange method. So Newton method, we got the final answer is 70.7776%, and while Lagrange method, we got 70 and 7776%. So and the MATLAB and manual results are identical. So macam yang kita dapat tengok, both method tu dia dapat produce the same value, which is 70.7776%, and the result follows the increasing humidity trend. And Newton method is more efficient because more efficient when adding new data point. So as a conclusion, we can see that missing humidity value successfully recovered, and estimated humidity at 7 minutes is equal to 70.7776%, and it is suitable for greenhouse climate control applications. That's all from me. Let's move to the next presenter with chapter 6. Chapter 5.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amirul Amin Mu'minin bin Abdul Rahim. My number metric is 69986. Today we will be presenting our group assignment result for question 5.1 regarding the RC charging circuit. Based on the given first order differential equation is 12 equal to 0.04 dV divided by dt plus 0.08V. So our first step is the manual conclusion to arrange the equation to get the slope function dV divided by dt equal to ftv. By dividing the entire equation by 0.04, we obtain our simplified derivative equation. It means ftv equal to 300 minus 2V. We are given the initial condition where the capacitor voltage is 0 at time 0, meaning V0 equal to 0, and we are using a step of H equal to 0.2. Our primary objective is to optimize the capacitor voltage at the T equal to 0.6 using two different numerical methods. So first look at the yellow method. This method approximates the net voltage point by using only the initial slope of each interval through the value V1 plus 1 equal to V1 plus H darab FT1 V1. In interval 1, T equal to 0 to 0.2, evaluating our initial function f00 giving us slope of 300. Therefore, the voltage V1 at T equals to 0.2 is calculated as 0.02 divided by 300 equal to 600,000 volt. In interval 2, T is 0.2 equal to 0.4. Substituting 60 volt into our slope function gives us a new slope of 118. The resulting voltage V2 at the T equal to 0.4 is 60 plus 0.2 divided by 118, and we get the 69,000 V. Okay, so we moving to the interaction tree. It means like a T equal to 0.4 go to 0.6. For the Euler method, the slope is updated using the 69V value. The heading of a scope is 108. Thus, the final estate capacitor voltage at the T equals to 0.6 using Euler method is 117.1.6000V. Now we look at our second numerical method approach, which is Huygens method. This method significantly improves the crude estimation of the Euler method by applying a predator corrector approach. Instead of relying on a single initial slope, it averages the slope the beginning at the predicted slope at the end of the interval. So for the first interval, t equal to 0 to 0.2, we first calculate the predicted voltage using Euler formula, which giving us Vp equal to 60V. We evaluate the slope at the prediction point, giving f equal to 0.2 and 16, we get the 118. Finally, we correct our estimation by taking the average of internal slope, is mean 300, and the predicted slope 118. This calculation reward us with a more refined voltage value for V1, which is 48V. Okay, so we continue offhand and MATLAB solution. Okay, the Huygens method continues with the same rigorous predator correction step of the remaining interval. For the second interval, t equal to 0.2 go to 0.4. The predictor and corrector step are calculated using the update slope, giving us voltage value of V2 equal to 0.6444V. For the final interval, t equal to 0.4 go to 0.6. The action same cycle is repeating using the slope using the Huygens method, giving us actually 102.8352V. Okay, now let's look the final output, our MATLAB simulation, and compare them with a manual work. So firstly, the Euler method finish with a voltage of 117.6000V. The Huygens method finish with a voltage value of 102.8352V. The analytical extent solution provide the absolute true value of 104.8209V, which round to 104.6950V if evaluate using the standard 4-dimensional rounding in the report final table. Next, let's analyze the true percent relative error for both method. The error is computed using the standard value is error equal to exact value minus numerical value divided by exact value kali dengan 100. So the Euler method get a relative high true error of 12.1914%. On the other hand, the Huygens method yield on standing small true error of only 1.8943%. So, looking closely at the data, we can confidently conclude that the Huygens method is vastly superior in the term of accurate and precision where compared to the Euler method for this RC charging circuit simulation. The Euler method suffers from a much larger error because it uses only a single slope at the beginning of each internal. So that concludes my presentation for group 4, and thank you very much.
My name is Shahazrin, number battery S72989. Today our group will discuss about question 6.2, which involve analytical of the current related quantity in a power electronic circuit represented by the integral of the function square root 4 plus x squared from 0 to 2. To solve this complex definite integral potential and analytical, we implemented the composite trapezoidal rule across multiple subintervals and further enhance our precision using rhomboid integration. Let's begin with our first manual step shown on the left of the screen. For a single subinterval where n equal to 1, the step size h is calculated as 2, yielding a baseline integration value of 4.8284. When we increase our grid density to n equal to subinterval, our step size reduced to 1, creating intermediate data coordinate. Summing this value using the multi-point trapezoidal formula gives us a more refined approximation of 4.6503. Simultaneously, with our MATLAB implementation on the right side of the screen, here we initialize our integration boundaries. Call our custom trapezoid rule script from both n equal 1 and n equal to 2 to validate our manual proof. As we move to the next phase of our project, we push our manual calculation further by dividing the integration zone into n equal 4 distinct subintervals. As shown on the left hand, this shrink our step size down to 0.5, expanding our evaluation data array across 5 boundaries points, and proceeding this manual sequence step by step result in much higher trapezoidal value of 4.6060. However, instead of stopping there, we utilize this multi-tiered trapezoidal output to build a Rhomberg integration table. The value obtained from n equal 1, 2, and 4 are mapped directly as our base level 0 Rhomberg column vector, represented as R10, R11, and R20. To eliminate predictable mathematical truncation error, we apply the Richardson extrapolation formula. Manually calculating our first outer tier cell, R21 gave us an upgrade numerical projection of 4.5909. To automate this structural grid workflow without tedious manual bookkeeping, look at our corresponding MATLAB script on the right. This portion of code systematically arranges our raw multi-point trapezoidal value right into a structured matrix array, ensuring our data layout seamlessly prepare for higher order recursive column processing. Continuing with our computational progression, we complete the final tier of our manual Rhomberg table. By extrapolating our share interval boundaries, we calculate R22 to be 4.5912 and ultimately resolve our final highest order Rhomberg approximation R32, which evaluates cleanly to 4.5912. On the right side of the screen, we can verify our exact program mechanism. We construct an independent local function named trapezoidal to compute composite mesh point loops. When we execute the full script, the program appears on the live command window logs seen in the MATLAB. MATLAB output and automate evaluation tracking our manual structure perfectly, showing 4.284, 4.6503, and 4.6059 for our progressive trapezoidal step, and culminating the automated Rhomberg output to 4.5911. The microscopic difference of 0.0001 between our manual calculation and the MATLAB environment comes down entirely to floating point rounding precision within the software engine. This confirms that our analytical formulas match up seamlessly with a background automated calculation. setting the stage for us to execute a rigorous error analysis against the true mathematical benchmark value. Finally, let's analyze our definitive error analysis and comparison of results. Given that the true value of our circuit integral is mathematically fixed at 5.91600, we computed the percentage true error for both approaches. As compared in our summary table, the trapezoidal rule and equal 4 yields an approximate of 4.6060, resulting in a percentage true error of 22.14%. Meanwhile, a rhomb integration method estimates the value 4.5912, producing a slightly larger true error percentage of 22.39%. Looking at the right side of our screen, you can see our automated MATLAB logic executing this exact error equation and running a conditional assessment statement. Based strictly on this numerical result, the trapezoidal method with n equal 4 proved to be more accurate for the specific problem because it holds a lower error percentage compared to rhomb integration. While rhomb integration is theoretically designed to clear out truncational error via systematic extrapolation, it heavily relies on smooth behavioral curve. For this specific function across a wide interval, the baseline trapezoidal step happened to fall structure close to true total area. This concludes our presentation demonstration that our manual proof and MATLAB are fully verified. Thank you.